Hello, everyone. I'm trying to, the purpose of this video is to show you the basic workflow for fitting data absorbance melting curves with MeltR. So the first thing we need to do is get our data formatted. So if we look here, MeltR needs these columns. They have to be named precisely, and I like to save them in a CSV file. Here we have sample, path length, temperature, absorbance. And note that this data is tidy formatted, which means each observation has a column, and each column is a different variable. We don't, for different samples, we just keep pasting that in below the other samples. So we're going down, it goes like 2, 3, 4, so on and so forth. We don't start pasting in new columns for different samples. So after we do that, we can go ahead and save this as a CSV. Make sure you save it as a CSV. And then we're good to go for the MeltR part. I'm going to show you how to do this in RStudio. I like it a lot because it's a nice little wrapper. And the first thing I'm going to do is make a new file. And once I've made my new file, I'm going to take that file and save it in the same directory as my data. And I'm just going to call this example script.r. Okay. So now that I have my script saved in the same directory as my data, same file folder, I'm going to go ahead and find the right place in the computer. You know, we have to tell R where it should be working. And the easiest way to do this for a newbie is just to go session, set working directory to source file location. After that's done, it runs in your R console this little line of code that tells it the right place to go in the computer. I like to copy it and then paste it into my script. That way, when I open up this script later, it'll go to the right place. Okay, so next thing we're going to do is load in packages. This is telling R what commands we need to run. If you haven't already, you need to read the instructions for installation on the website where you probably found this link. But I already have MeltR installed. So I'm going to go ahead and type library MeltR, and this will expose all of the commands that I want to run to the computer. Another thing I want to do is use the tidyverse, because I like to use that for checking the data, which is really important. So next, we're going to go ahead and load in the data. And to do that, we're going to go df equals read CSV. And now I need to figure out what file to put in here. So I'm going to go ahead and type list.files. And I can see the name of my data file right here. And I'm going to go ahead and copy that and put it there. Up next, I want to check data. The number one problem that people have with MeltR is trying to fit data that doesn't really agree with the model. We want to make sure we have high quality data before we're putting it into MeltR. So we're going to go ahead and check the data. First thing we can do to check it is we can look at the header. And we can see we have the right data. We've got sample, path length, temperature, absorbance. Up next, I'm just going to use the tidyverse to plot it real quick. So I'm going to type ggplot data is df. If you type this exactly, you'll get a nice plot for your data. X equals temperature. Y equals absorbance. And then I'm going to make the color of the series correspond to the sample. Okay. And I'm actually going to make sure I'm going to turn the sample column into a factor. And then I want to see a line plot. So I'm just going to go ahead and type geom point. Let's see, I'm getting a little error in my script. I don't know why. I think we're fine. Yep, we were fine. So when you run that, a little plot will pop up, and you can see that the data looks pretty good. I just want to really, so there's these very long upper and lower baselines, and I probably don't want to include these in the fits. Do you see, like, at very low temperatures, how it's kind of curving over? So I'm just going to quickly put some lines on the plot to figure out what temperature range I want to fit. So I can use, so I've added a plus sign, and now I'm going to go geom B-line. And here I just have to give it x-intercepts. So x-intercept equals, I'm going to make a vector, and I think we should fit 25 to 80, because I've done this before. So now I've got the same plot, and I can see that I'm going to have nice baselines if I fit the range 25 to 80. And the data looks good. So I think we're good to put it in MeltR. So now we're going to fit the data with MeltR. And this is going to have two steps, MeltR A, and we're going to follow that with an auto baseline trimmer. If I can manage not to keep hitting my caps locks. All right, so the first thing I want to do, because MeltR A does a lot of things, and I can't remember what it does, so I always look at the help manual and I say MeltR A. And I've got the help manual, help file pops up, and I can see the usage and all the different arguments. And there's a lot of default settings, and I'm going to worry about those later. But for now, I know that I need to specify the data set. So I'm going to go MeltR A and then df for data frame, which we loaded in here. And then the next argument I'm seeing is blank. And I know from experience that there's a blank in this data set, and it's sample number 1. And then I need to supply, anytime we see an argument without a default, we need to supply it. And so we need to supply the nucleic acid, and we're going to go C, and it's an RNA. And then we tell it what sequences are in there. If this is like a homoduplex, you only need to enter that sequence once because it's self-complementary. But since this is a heteroduplex, this particular data set, I need to enter 2 different sequences. So C, G, A, G, G, U. And then I'm going to go A, C, C, U, 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 C, G. So that's all we have to do to specify what the nucleic acid is. And then the last thing that doesn't have a default setting is the molecular model, or M model. So M model, and I don't remember what all the options are. So I'm going to go ahead and scroll down the help file until I get to the molecular model. It says the molecular model you want to fit. The options are monomolecular 2-state, monomolecular 3-state. That's not a real option. That's something I'm working on. And then heteroduplex 2-state and homoduplex 2-state. And this is a heteroduplex 2-state RNA. So I'm going to go ahead and copy it and paste it. And I'm just going to see if it runs. And it did fit the data. I've got my results for the individual fits. And then I've got the summary of the 3 methods that MeltR uses to determine thermodynamic parameters, 1, 2, 3. And then I have the percent error between the methods. And this is a little high. So I'm going to go ahead and see if you remember this plot, which we can pull back up. I would like to apply this baseline trimming. So I'm going to go ahead and go back to my help file. I see that the fit-tease argument is what I need. I can supply a list, following these instructions, but I'm just going to use a constant range. So I'm going to say fit-tease equals C 25 to 80. Okay. And I'm going to rerun it. And I get a similar error between the methods. Now, you could play with the baseline trimming, you can play with the other settings, but I like to use the baseline trimmer in MeltR. So to use the baseline trimmer, I need to make a MeltR fit. So MeltR fit equals that. Now I have this object. So if I look what's in the object, I can see all kinds of stuff. And you can read the manual to figure out what's in it. You can also read the help file, it's down here. But why this is important is if we look at the BL trimmer help file, we see the first thing we need is a MeltR fit. So we're going to say, trimmed fit equals BL trimmer. And then, oops, I can't have a space here. I'm going to say save. Results equals all. You can also apply this save results argument here in the MeltR part. Since I've missed that, I'm going to circle back to that. But basically, this will print some pre-canned results when we run it. So I'm going to rerun this. Now I'm going to run this, and we're going to wait on the baseline trimmer. So it says you're trying to test 1,000 possible combinations. Do you think this is possible? I do. The number of different randomly trimmed baselines you're going to go ahead and test is going to be dictated by how many you enter here. So this argument basically exists to tell somebody, oh, you just tried to get it to run 9 billion tests. We're going to be sitting here for a while. But 1,000 samples happens in about a minute, and we can see it's getting there. So it's fitting 1,000 combinations of 6 different baselines per sample. And now it's decided which ones it likes best, and it now passed it back to MeltR. And now it's fitting that. Okay, we got our results. We got a little table with the different methods. And then we have thermodynamic parameters with 95% confidence intervals for each method. We also have a fractional error between methods. We can see after we used a baseline program that it's very low, indicating that the quality of our data set is very high. So now we're going to look at some of the pre-canned figures for MeltR and talk about how to interpret those. So you can see our directory was empty and now it has a whole bunch of stuff. Let's first focus on the stuff that's made by MeltR A, which is this stuff. So we've got like a depiction of method 1. We've got a depiction of method 2. And then we've got CSVs containing the results. You can open these in Excel, go in, look at our thermodynamic parameters, copy and paste them, you know. And then we also have the results from the baseline trimming analysis. So if we open this CSV, we can see our results. And then we, last but not least, we have an ensemble analysis. And I'm actually going to take some time and try to explain what's happening here. Okay, so there's a lot going on here. So basically, the baseline trimmer fits a lot of randomly generated baseline combinations and decides which baseline combinations create the most consistent thermodynamic parameters across the data set. And you can use 3 different methods. The default is 3, method 3. And so basically method 1 looks at differences between samples in the individual fits, where each curve is fit one at a time. And it looks at all of these, and it says for 1,000 baselines, and this is this distribution. And these blue bars are what was passed to the final ensemble. So the data that makes it into the final thermodynamic parameters. The same thing happens with assess method 2. It looks for agreement between MeltR method 1, which is the individual fits, and MeltR method 2, which is 1 over TM versus LNCT. And it picks, the gray bars represent 1,000 different baseline combinations. And the blue data represents what's past the final ensemble. And then by default, the baseline trimmer uses method 3, which uses a statistic called the error distance, which is basically the length of these lines. And it combines method 1, assess method 1, and assess method 2. And that's what happens by default. That's why these data points are blue. So even though we're showing assess method 2, these blue data points were chosen using assess method 3. And if you use a different assess method, you can change that to 1 or 2, and it will, in the help file, shows you how, and it will change the colors and change which optimum baseline combinations are being used in the final analysis. If you're going to start changing parameters, you need to start worrying about two-statedness. And if we look here, for a approximate two-state folding helix, this distribution is going to peak below 10%. There is a positive control that we describe in the manual, that is a non-two-state melting sequence. And if you need to change the baseline trimming parameters, you can use that positive control and look at this distribution on the non-two-state sequence, and it will peak at about 15%, indicating that it's non-two-state. So yeah, that's the basic workflow. I can save my script. Okay, thank you.